right, these are the work, power, and energy notes, part 3. So we have covered basic work, basic power, and basic energy. And now in part 3, we're going to talk about the law of conservation of energy as well as the work energy principle. Okay, so the work energy principle is roughly says that work of a resultant external force on a body is always equal to the change in the kinetic energy of that body. So we could say that work is equal to change in kinetic energy. And so we would have our kinetic energy final minus our kinetic energy original. So right here, there's an applied force. It does move a displacement. So remember, we could also replace this W right here with F times D, and that would equal my 1/2 mv F squared minus my 1/2 mv O squared. Notice these velocities are different, so I have a different amount of kinetic energy, and that was because of the fact that I applied a force through a certain distance. So what average force is necessary to stop a 16-gram bullet traveling at 260 meters per second as it penetrates into wood at a distance of 12 centimeters? Well, first of all, I have to change grams to kilograms and centimeters to meters. So I'll divide by 1,000 and get that in kilograms. My distance, I'll divide by 100 because there's 100 centimeters in a meter. And then I have a velocity. Okay, my final velocity is a stop because it says to stop a bullet. All right, so I know that my work is equal to my change in kinetic energy, and I know change in kinetic energy is my final kinetic energy minus my original kinetic energy. So I also know that work is force times displacement. So I can say force times displacement equals 1/2 mv F squared minus 1/2 mv O squared. Since my final velocity was 0, I could cancel the entire kinetic energy expression final out because anything multiplied and divided by 0 is 0. Okay, so then I would end up with a negative 1/2 mv O squared divided by D to get my force by itself. So then I could plug in those numbers. I know my mass, I know my velocity. I just did my half by dividing by 2, and then I have my distance as 0.12. So I would end up with a negative 4,506.67 newtons. Which makes sense. This force should be negative because it's a stopping force. So it is a vector, so it should be going in the direction of, and since we're slowing down, that it's decelerating, so it's a negative acceleration, so it should be a negative force. All right. I could also say that the work energy principle works for the change in potential energy as well. So the work of a resultant, again, external force on a body is equal to the change in that gravitational potential energy of the body. So I could say that work equals the change in potential energy, or I could say that work equals the F times the change in D. Okay, which is really what that mass times gravity is F, and HF minus HO is just my change in D. Okay? Now, the law of conservation of energy states that energy can't be created nor destroyed. It can only be transferred from one kind to another. But overall, the total amount has to remain the same. So whatever energy you start with, you have to end with. Okay? So for mechanical systems involving conservative forces, which is all we will deal with, the total mechanical energy equals the sum of the kinetic and potential energies of the system. So what we can always say is the potential energy at the beginning plus the kinetic energy at the beginning has to equal the potential energy final plus the kinetic energy final. Okay, so notice these values are always going to be the same as long as we have conservative forces, which until we get to this, we have conservative forces. Here we have frictional force. It's a non-conservative force, so some of the work comes out, and that's why we end up with negative work. But we are not going to take it into that information. So really all you need to remember is the energy before has to equal the energy after. Okay, so here I have all potential energy because my kinetic energy is 0 because it's sitting still. Here I have half kinetic energy and half potential energy because the height is in the middle. so it still has some height, so it has potential energy, but those added together have to equal this. And then here my height is 0, so my potential energy would be 0, and all of it would be kinetic. Because again, all of this kinetic energy at the bottom has to equal all this potential energy at the top. Okay, so here we have our kinetic energy and potential energy switch depending on where we're at, but the total amount of energy ultimately stays the same the entire time. Okay. We have another example here, again, for mechanical systems. The total mechanical energy equals the sum of the kinetics and the potentials. Okay. So I have a 40 kilogram pendulum ball. It's pulled to one side until it is 1.6 meters above its lowest point. I want to know its velocity is going to be as it passes through its lowest point. I know its mass. I know its height. Okay, and I know the energy at the beginning has to equal the energy at the end. Okay, so I know that over here it has, right here it stops. So it has, I have to look, do I have kinetic energy at the beginning and do I have potential energy at the beginning? Well, it's not moving, so I don't have any kinetic energy at the beginning. But at the very bottom, I also know that my height is 0. So at the very bottom right here, if I know the height is 0, then I don't have any potential energy at the bottom. So I'm going to be able to cancel those values out. So I'll be able to do that. So now I'm really just going to say the potential energy at the beginning has to equal the kinetic energy at the end. So then I'm going to be able to expand that out and say mass times gravity times height at the beginning. I could have an I there instead. Has to equal my kinetic energy at the end, which is mvf squared. Well, you might notice that there's an m on both sides. So guess what you get to do with that? You get to cancel out the m. All right? So now you have your GH original equals 1/2 VF squared. So if I want to find the VF, I'm going to multiply both sides by 2 to get rid of the half. So I'm going to come over here and multiply this by 2. So now I have 2 GHO equals VF squared. And to get rid of the squared, I'm going to take the square root. So I would do square root of 2 GHO equals VF. This formula actually ought to look really familiar to you because we had a formula that was VF squared equals VO squared plus 2AD back when we did kinematics. And if this is 0, then this is the same formula. Okay, and now A is just gravity and H is just D. So it's something that we've already dealt with before, which makes it, fun to see it again because it wraps back around to some of the information that we already learned. So we're able to do that, and I showed you that, and we manipulate the equation, and I showed you that. So then when we plug in that we know the 2, we know gravity is 10, and we know the height is 1.6 meters, we can find out that the velocity is 5.66 meters per second. Okay, and if we really watch carefully, right as it passes through the bottom, you can see that it says 5.66. It's like 5.67. So, kind of cool. All right. So, if friction forces are negligible, which we're always going to say they are, the coaster has a speed of 2 meters per second at point A. I want to know what its speed is going to be at point B. So I know the speed is at A is 2. I'm going to tell you the height at A is 0.8. Then I'm going to tell you the height at B is going to be 0. Okay, so at point A, I have both kinetic and potential energy because I have a height and I have a velocity. And at point B, I'm going to have just kinetic energy because if the potential energy is, if the height is 0, the potential energy is 0. So I could actually write my formulas out like this. Again, I know this is 0, so that will go away. There's an m in every one of those expressions, so I can also cancel out the m. All right, then I know the height of A, I know gravity, I know the velocity at A, and I'm looking for the velocity at B, which I can then solve for by doing this formula. That's the manipulation of that rearranged. Okay, so 2 squared plus 2 times 10 times 0.8 gives me an answer of 4.47 meters per second. All right. I can continue with this example, and I can now say, what will its speed be at point C? Well, the height at point C is going to be 0.5 meters. So at point C, I know that it has potential and kinetic energy if it has a height and a speed. So I could go back to my original. Again, I could cancel all my m's out because every expression has an m. And I can plug values in and rearrange, and it'll look kind of complicated, but I'll tell you, if you plug your numbers in first and then simplify and rearrange, it makes it a lot easier. Okay, because that's what it looks like, and like I said, that looks kind of confusing always in my opinion. So it really does multiply out to be the square root of 2g change in h. Let me do it this way. HA minus HC plus VA squared. That's really what it works out to be. So that's a little bit friendlier to look at. But we know the HA, we know the HC, we know the VA. So we can solve, and you should get 3.16 meters per second. Okay? All right, so that wraps it up as far as what we are covering in notes. Again, if you have any questions, please let me know in tutorials.